Hey everyone. So today we're going to look at the wave speed equation and understand how fast a wave moves, or more specifically, how fast the energy is propagated through a wave. So when we talk about this, we're going to talk about the wave speed or wave velocity. Okay, and that's how fast the wave crests or any other part of the wave moves. And so it's not the same as the velocity of a particle in the medium. So remember, the particles in a medium just go up and down with the wave. They don't travel forward. The wave doesn't carry particles with it. The wave is carrying energy. So when we talk wave speed, we're talking about how fast that energy is being transferred from one location to another. There's a couple of ways, two ways to calculate the speed of a wave. So let's imagine for a second that we have a wave that's traveling. Okay, and we'll say that it's going to be a couple wave crests. We'll say that it's moving to the right. Okay, one way we can measure the distance of the wave is we can look at our old definition of velocity. Okay, or speed is distance, change in distance, divided by time. So, for example, if we measured a point here. Okay, and we watched this wave, and we watched this wave as it moved along, and it moved along, and it moved along, and we measured another point over here. Okay, and we took this distance that it traveled. We found a change in distance from this point to this point, and we calculated how long it took to do that. We could calculate the speed of the wave that way. So just looking how fast it travels to a particular point. The other way to do it that we're going to talk about, get rid of this line, is by using the wavelength. So let's imagine for a second that we station ourselves here and we're watching these waves pass by. So we're watching dozens and dozens of waves pass by. And we set up a line. Okay, and we keep track of how many waves, we keep track of how many waves pass by this point in a given amount of time. Okay, so this is kind of similar. Imagine someone running a track and field, and they run 4 laps around the track. Well, each lap is a cycle, just like each wavelength would be a cycle, and we could get the period of the person and calculate their velocity that way. So by watching how many waves pass by and keeping track of the wavelength and the period, we can calculate the wave speed by taking the wavelength, which is measured in meters, so a distance, divided by the period of the wave, which is time. So again, 2 different ways to calculate it. And another equation that stems from this one, because we know that the frequency is equal to 1 over the period, so we can actually substitute this in, and we get what we normally refer to as the wave speed equation, the wavelength times the frequency of the wave in hertz. Okay, so this is our equation we're going to use. So any of these 3, depending on the situation. Again, the first one is looking at the total distance a single wave moves and how long it takes it to get there. The second equation is by examining the wavelength of the wave and how many of those are passing by in a particular amount of time, so getting the period, or we can substitute and get the frequency. So let's take a look at a couple of examples for this. Example 1, we have a hiker. So a hiker shouts toward a vertical cliff 685 meters away, so the sound is going to go toward the cliff, bounce off of the cliff, and come back to the hiker as an echo. Okay, we have our wavelength of sound. What is the speed of sound in air? So in this case, let's just draw a quick sketch of what's happening. So we have someone who's yelling. Okay, here comes their sound waves coming out of the person, and we have our cliff face, which is 685 meters away. Okay, so the sound travels out, hits the cliff, and bounces back to the person, and they hear that echo. So what we know is that our distance, okay, that the sound is traveling is not 685, but 685 times 2 will be the total distance that the sound has traveled before the echo is heard. Our time is 4 seconds. And we're looking for the velocity. We have the wavelength as well, but knowing the distance that the wave traveled, and so how long it took that first crest to go from you to the cliff and back to you, we can use our regular speed equation, change in distance over time. Okay, and we get 685 times 2 divided by 4, giving us a speed of the wave as 343 meters per second. Okay, so the second part of this question, so 343 meters per second, what is the frequency of the wave? Well, now that we have the speed of the wave as 343, and we know the wavelength, 0.750 meters, given to us in the question, we can use that and use our wave speed equation, phi equals wavelength times frequency, to calculate the frequency of the wave. So we have our velocity is 343 times our wavelength, 0.750 f. So dividing 343 by 0.75, we get a frequency of 457 hertz. Remember, a hertz is a unit of 1 over a second. And the last question, what is the period of the wave? So now that we have our frequency from the previous question is 457. The period is pretty easy to find because we just use the fact that the frequency is equal to 1 over the period. I should say we're looking for period. So we're going to want to use periods equal to 1 over the frequency, rearrange that. 1 over 457, or that the period is equal to 2.19 times 10 to the negative 3 seconds. Okay, let's take a look at another example. So example 2. Water waves have a wavelength of 3.2 meters and a frequency of 0.78 hertz. So we have water. At what rate does a boat bob up and down on the water? Okay, so here's my water waves. Okay, we're going to say that they're traveling in this direction. Here is my boat sitting on top of the water waves. So as the wave travels, remember the boat's not going to move from this position. The waves don't carry the boat back and forward. Okay, it's going to stay here and just move up and down on these waves. So if the waves are traveling at a frequency of 0.78 hertz, the question is, how fast is the boat moving up and down? The boat isn't contributing to the frequency. It's only the waves that are causing the boat to move. So if the waves are moving at a frequency of 0.78, then in this question, the boat would also be moving at a rate of 0.78 hertz. So it's moving at the same rate as the waves. Now the second part of this question, if the boat starts moving into the waves in the opposite direction at a speed of 5 meters per second, at what rate will the boat bob up and down now? So now we have a little bit of a different situation here. I'm going to draw my waves again. And here is my boat sitting on top of the waves. And we're going to say again that the waves are moving this way. Now normally if the boat was not moving, okay, it just bobs up and down at the same frequency as the waves. But now the boat is moving in the opposite direction. So if you think about this, if the boat's standing still and the waves are crashing into the boat, now the boat is moving into the waves, so it's going to be crashing at a higher rate. So we should get for this answer an increased frequency. Since we have two objects moving with different speeds, we're going to have to use relative velocities to solve this one. So let's start by getting the velocity of the water. Since we have all that information, so that's going to be equal to the wavelength of the water times the frequency of the water, which is 3.2 times 0.78. That gives us a wave velocity of 2.5 meters per second. Okay, so again, that's how fast the water would be hitting the boat if the boat wasn't moving. But since the boat is moving into the waves, it's going to be hitting at a faster rate. So for the relative velocity, we take the velocity of our boat crashing into the waves and add our velocity of the water crashing into the boat. Okay, so that's, what was the boat? 5 meters per second plus 2.5 meters per second is 7.5 meters per second. So again, since it's moving into the waves, it's crashing at a higher rate. So we're going to appear to be hitting them at a higher speed. Then we can use that speed to find the frequency of the boat. So the relative velocity is just going to be equal to again, the wavelength. The wavelength isn't changing. Even though the relative frequency or velocity is different, the wavelength is still the same for the water, and times the frequency. So the relative velocity, we have 7.5 is equal to the wavelength times, we know our wavelength is 3.2 times our frequency, and we end up with a frequency of 2.3 hertz. Okay, so this is larger than our initial frequency, again, because the boat is heading into the waves, so it's going to be colliding with them and moving up and down at a faster rate. For our last example, we have water waves in a lake are traveling at a speed, are traveling 4.4 meters in 1.8 seconds. The period of oscillation is 1.2. What is the speed and wavelength of the water waves? Okay, so here's where we have to be careful. We have two different times, so we have to distinguish which time is the time and which time is the period of the waves. Okay, so in this first one, water waves in a lake travel 4.4 meters in 1.8 seconds. What's that saying? If we just have one wave, okay, here's our lake. So this wave travels a distance of 4.4 meters in 1.8 seconds. So that's our time. So we can use our regular velocity formula along with that time and distance to find the velocity of our wave. The period of oscillation is 1.2. Again, that's how fast this wave is repeating. Okay, not the time of its travel. So what is the speed and wavelength of the water waves? So take speed is equal to distance over time. Okay, our distance 4.4 meters in 1.8 seconds, and we get a velocity of the wave of 2.4 meters per second. So that's our wave speed. And then it asks for what is the wavelength. So for the wavelength, we can use our wave speed and our period. So we can use that our speed is equal to wavelength divided by the period, which is 2.4 is equal to wavelength divided by 1.2. And we get a wavelength of approximately 2.9 meters. Okay, and that's it for everything on wave speed.